When sizing conductors for a transformer, accuracy is paramount to ensure safe and efficient operation. Let's delve into the calculations and considerations for a 100 kVA 480 volts delta to 120/208 volts Y three-phase transformer. We'll address both the primary and secondary conductor sizing, as well as overcurrent protection. Firstly, let's examine the primary conductor sizing. To determine the primary current, we use the formula kVA divided by volts divided by the square root of 3. In this case, 100 kVA divided by 480 volts divided by the square root of 3 equals 120 amps. Now, referring to National Electrical Code Table 310.16, we can find the appropriate conductor size. For THHN wire with 75 degrees Celsius terminations and 90 degrees Celsius insulation, a 1/0 THHN conductor is rated to carry 125 amps. Therefore, a 1/0 THHN conductor is sufficient for the primary side. Secondly, let's discuss the secondary conductor sizing. To calculate the secondary current, we use the same formula kVA divided by volts divided by the square root of 3. However, this time we use the secondary voltage. 100 kVA divided by 208 volts divided by the square root of 3 equals 277 amps. Again, consulting National Electrical Code Table 310.16, we find that a 500 mcm THHN conductor with 75 degrees Celsius terminations and 90 degrees Celsius insulation is rated to carry 380 amps. So a 500 mcm THHN conductor is adequate for the secondary side. Now let's move on to primary overcurrent protection. The National Electrical Code permits sizing the primary overcurrent protection at up to 250% of the primary current if secondary protection is provided. Since the overcurrent protection device on the connected machine is unknown, we must assume it could be rated at or above 250% of the secondary current. In this scenario, we should size the primary overcurrent protection at 250% of the primary current. The calculation is 120 amps multiplied by 250%, which equals 300 amps. This means the primary overcurrent protection should be rated at 300 amps. Consequently, the primary conductors must also be rated for the full 300 amps. This necessitates the use of a 400 amp tap box to accommodate the overcurrent protection. To summarize, the correct wire sizes are 1/0 THHN for the primary conductors and 500 mcm THHN for the secondary conductors. The primary overcurrent protection should be rated at 300 amps, and the primary conductors must be rated for 300 amps as well. Remember to always consult the latest edition of the National Electrical Code and local regulations for the most up-to-date requirements. Understanding transformer conductor sizing and overcurrent protection is crucial for electrical safety and compliance. By following these guidelines and performing accurate calculations, you can ensure a reliable and safe electrical installation. Several factors influence the selection of wire size and overcurrent protection for transformers, and it's crucial to consider these factors to ensure a safe and efficient electrical system. Firstly, conductor ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. This is determined by the conductor's material, size, insulation type, and installation conditions. National Electrical Code Table 310.16 provides ampacity ratings for various conductors based on these factors. Secondly, voltage drop is the decrease in voltage along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Thirdly, overcurrent protection devices, such as fuses and circuit breakers, are designed to protect conductors and equipment from overloads and short circuits. The National Electrical Code specifies the maximum overcurrent protection rating for conductors based on their ampacity. Transformer primary protection is generally addressed in National Electrical Code section 450.3. It allows for different protection schemes based on transformer size and the presence of secondary protection. If the transformer has secondary protection, the primary protection can be sized up to 250% of the primary current. Without secondary protection, the primary protection is typically limited to 125% or 150% depending on the transformer's impedance. Transformer secondary protection aims to protect the secondary conductors and connected equipment from overloads and short circuits. The size of the secondary overcurrent device is determined by the ampacity of the secondary conductors and the requirements of the connected equipment. National Electrical Code Article 240 provides detailed rules for overcurrent protection. The impedance of a transformer affects its voltage regulation and fault current. Higher impedance transformers have better voltage regulation but lower fault current, while lower impedance transformers have the opposite characteristics. Understanding the transformer's impedance is essential for coordinating overcurrent protection. Installation methods, such as conduit type, ambient temperature, and conductor bundling, can affect the ampacity of conductors. The National Electrical Code provides adjustment factors for these conditions. Higher ambient temperatures and conductor bundling reduce the ampacity of conductors, while certain conduit types can improve heat dissipation. Continuous loads are loads that operate for 3 hours or more continuously. The National Electrical Code requires that overcurrent protection devices for circuits supplying continuous loads be rated at 125% of the continuous load current. This is to prevent nuisance tripping of the overcurrent device due to prolonged heating. The available fault current at the transformer's terminals determines the interrupting rating of the overcurrent protection devices. The interrupting rating is the maximum fault current that an overcurrent device can safely interrupt without failing. Overcurrent devices must have an interrupting rating equal to or greater than the available fault current. The coordination of overcurrent protection devices involves selecting devices that will trip in a coordinated manner to isolate a fault without disrupting the entire electrical system. This is typically achieved by using time current codes to ensure that upstream devices trip before downstream devices. When selecting wire sizes and overcurrent protection for transformers, it's essential to consider all of these factors and consult the latest edition of the National Electrical Code and local regulations. Performing accurate calculations and following best practices will help ensure a safe, reliable, and efficient electrical system. For a 100 kVA transformer with a 480 volts primary and 120/208 volts secondary, the primary full load current is approximately 120 amps and the secondary full load current is approximately 277 amps. When sizing the primary conductors, we must consider the calculated load, conductor ampacity, voltage drop, and overcurrent protection requirements. According to National Electrical Code Table 310.16, a 1/0 AWG-THHN copper conductor has an ampacity of 150 amps at 75 degrees Celsius. This conductor size is adequate for the 120 amp primary current, but we must also consider voltage drop and overcurrent protection. To minimize voltage drop, we can increase the conductor size or use parallel conductors. For the primary overcurrent protection, National Electrical Code Section 450.3 allows for overcurrent protection up to 250% of the transformer's primary current, provided that there is secondary protection. In this case, 250% of 120 amps is 300 amps. Therefore, we can use a 300 amp overcurrent device on the primary side, and the 1/0 AWG-THHN conductors are adequately protected since they have an ampacity of 150 amps. When sizing the secondary conductors, we must also consider the calculated load, conductor ampacity, voltage drop, and overcurrent protection requirements. According to National Electrical Code Table 310.16, a 500 kcmil THHN copper conductor has an ampacity of 380 amps at 75 degrees Celsius. This conductor size is adequate for the 277 amp secondary current, but we must also consider voltage drop and overcurrent protection. Again, to minimize voltage drop, we can increase the conductor size or use parallel conductors. For the secondary overcurrent protection, National Electrical Code Section 240.4b allows us to use the next highest standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device size. In this case, we could use a 300 amp overcurrent device to protect the 500 kc mil-THHN conductors. However, it is essential to ensure that the overcurrent device protects the connected equipment from overloads and short circuits. In summary, the recommended conductor sizes for the 100 kVA transformer are 1/0 AWG-THHN copper conductors for the primary side and 500 kc mil-THHN copper conductors for the secondary side. The primary overcurrent protection can be up to 300 amps, and the secondary overcurrent protection can be 300 amps, provided that it protects the connected equipment. Always refer to the latest edition of the National Electrical Code and local regulations for specific requirements, and consult with a qualified electrical engineer or electrician to ensure safe and compliant electrical installation. Now let's discuss some real-world examples of how to apply these principles. Example 1 involves a small commercial building with a 75 kVA transformer. The transformer steps down 480 volts to 120/208 volts to supply power to lighting, receptacles, and HVAC equipment. The primary conductors are 4 AWG-THHN copper, protected by a 125 amp circuit breaker. The secondary conductors are 250 kc mil-THHN copper, protected by a 200 amp circuit breaker. Example 2 involves a manufacturing facility with a 500 kVA transformer. The transformer steps down 13.8 kV to 480 volts to supply power to machinery, equipment, and lighting. The primary conductors are 350 kc mil aluminum, protected by a 400 amp fuse. The secondary conductors are parallel 500 kc mil copper, protected by an 800 amp circuit breaker. Example 3 involves a data center with a 2000 kVA transformer. The transformer steps down 13.8 kV to 480 volts to supply power to servers, cooling equipment, and other critical infrastructure. The primary conductors are parallel 500 kc mil copper, protected by a 1200 amp circuit breaker. The secondary conductors are parallel 750 kc mil copper, protected by a 3000 amp circuit breaker. In each of these examples, the conductor sizes and overcurrent protection ratings were carefully selected to ensure a safe and reliable electrical system. The National Electrical Code and local regulations were followed, and qualified electrical engineers and electricians were involved in the design and installation. Let's also consider some common mistakes to avoid when sizing conductors and overcurrent protection for transformers. Mistake 1 is undersizing conductors. Undersizing conductors can cause overheating, voltage drop, and equipment malfunction. It can also create a fire hazard. Always calculate the load accurately and select conductors with sufficient ampacity. Mistake 2 is oversizing overcurrent protection. Oversizing overcurrent protection can allow excessive current to flow through conductors and equipment, leading to damage or failure. Always select overcurrent devices that are properly sized to protect the conductors and equipment. Mistake 3 is neglecting voltage drop. Excessive voltage drop can cause equipment to operate inefficiently or malfunction. Always calculate the voltage drop and select conductors that minimize voltage drop. Mistake 4 is ignoring ambient temperature. High ambient temperatures can reduce the ampacity of conductors. Always consider the ambient temperature when selecting conductor sizes. Mistake 5 is failing to coordinate overcurrent protection. Uncoordinated overcurrent protection can cause unnecessary outages and equipment damage. Always coordinate overcurrent devices to ensure that they trip selectively. Mistake 6 is neglecting continuous loads. Continuous loads require larger conductors and overcurrent devices. Always account for continuous loads when sizing conductors and overcurrent protection. Mistake 7 is failing to consult the National Electrical Code and local regulations. The National Electrical Code and local regulations provide specific requirements for electrical installations. Always consult these resources to ensure compliance. Mistake: it is not involving a qualified electrical engineer or electrician. Electrical work can be dangerous and complex. Always involve a qualified electrical engineer or electrician to ensure a safe and compliant installation. Finally, let's explore some advanced topics related to transformer conductor sizing and overcurrent protection. One advanced topic is the use of reduced-size neutral conductors. In some cases, the neutral conductor can be smaller than the phase conductors, provided that certain conditions are met. The National Electrical Code provides specific rules for sizing neutral conductors. Another advanced topic is the use of harmonic mitigation transformers. Harmonic mitigation transformers are designed to reduce harmonic currents in electrical systems. Harmonic currents can cause overheating, voltage distortion, and equipment malfunction. A third advanced topic is the use of solid-state overcurrent protection devices. Solid-state overcurrent protection devices offer several advantages over traditional electromechanical devices, including improved accuracy, reliability, and coordination capabilities. A fourth advanced topic is the use of arc flash studies. Arc flash studies are conducted to assess the potential hazards of arc flash events in electrical systems. The results of arc flash studies can be used to select appropriate personal protective equipment and to improve the safety of electrical workers. The fifth advanced topic is the use of power quality monitoring. Power quality monitoring involves measuring and analyzing various electrical parameters such as voltage, current, harmonics, and transients. Power quality monitoring can help identify and mitigate power quality problems that can affect equipment performance and reliability. The sixth advanced topic is the use of energy-efficient transformers. Energy-efficient transformers are designed to reduce energy losses and improve overall system efficiency. Energy-efficient transformers can save money on electricity bills and reduce greenhouse gas emissions. The seventh advanced topic is the use of smart transformers. Smart transformers are equipped with advanced monitoring, control, and communication capabilities. Smart transformers can provide real-time data on transformer performance and can be integrated with smart grid systems. These advanced topics require specialized knowledge and expertise. If you are involved in the design, installation, or maintenance of electrical systems, it is essential to stay up to date on the latest technologies and best practices. In conclusion, transformer conductor sizing and overcurrent protection are critical aspects of electrical system design. By following the principles outlined in this discussion and consulting the latest edition of the National Electrical Code and local regulations, you can ensure a safe, reliable, and efficient electrical system. Remember to always involve qualified electrical engineers and electricians in electrical work to ensure a compliant and safe installation. The National Electrical Code, or National Electrical Code, provides comprehensive guidelines for electrical installations, including those involving transformers. Adherence to the National Electrical Code ensures safety and compliance with industry standards. Article 450 of the National Electrical Code specifically addresses transformers and transformer faults. It covers requirements for overcurrent protection, grounding, wiring methods, and ventilation. Section 450.3 of the National Electrical Code deals with transformer overcurrent protection. It specifies the maximum overcurrent protection ratings for transformers based on their size and voltage. Section 250 of the National Electrical Code covers grounding and bonding requirements. Proper grounding and bonding are essential for electrical safety and to prevent electrical shock hazards. Article 310 of the National Electrical Code provides ampacity tables for conductors. These tables list the maximum current carrying capacity of conductors based on their size, insulation type, and installation conditions. Article 240 of the National Electrical Code covers overcurrent protection. It specifies the requirements for fuses and circuit breakers, including their interrupting rating and coordination. It is important to stay updated with the latest edition of the National Electrical Code as it is revised every 3 years to incorporate new technologies and best practices. Local jurisdictions may also have additional electrical codes and regulations that must be followed. Consulting with a licensed electrical engineer or electrician is recommended to ensure compliance with all applicable codes and regulations. In addition to the National Electrical Code, there are other industry standards and guidelines that may be relevant to transformer conductor sizing and overcurrent protection. The Institute of Electrical and Electronics Engineers, or IEE, publishes standards on various electrical topics, including transformers and power systems. The National Electrical Manufacturers Association, or NEMA, develops standards for electrical equipment, including transformers and overcurrent protection devices. These standards provide valuable information on the design, testing, and application of electrical equipment. Consulting these standards can help ensure that electrical installations are safe, reliable, and efficient. Furthermore, participating in continuing education courses and industry conferences can help electrical professionals stay up to date with the latest technologies and best practices. Ongoing learning is essential for maintaining competence and providing high-quality electrical services.